All right, let's keep going with some fun stuff here. U5A3 one variable analysis. So a little bit more about one variable. So we're just sticking with one variable for this part. Then we're going to go to two variable with the next video. So we're going to start off with a couple things. It starts off with the note starts off with box and whisker plots. We talk about quartiles and that sort of thing. Let's leave that. Kind of ignore that for a second. Come with me down here to histogram and distribution types because this will lead us into box and whisker plots, which are a little bit confusing, I think. But you'll be fine with them once you get your head around the slight nuances to them. Okay, so let's look at histograms and distribution types here. You're going to be making these on Google Sheets, so you don't have to do these by hand. These are a bit of a pain to do by hand anyway. So the first type is, so what happens is you make a histogram, right? So usually with a histogram, what you're going to have with the one variable data is on the side here, you're looking at frequency. So you got whatever you're looking at, or histogram for bus wait times, whatever this is in minutes, this is how common it is, okay? Later on, we look at something about CO2 release. This is how often it happens, okay? This is baseball average. This is how many people hit for that average. So up the side is some sort of frequency, okay? Usually just counted, but something as a percentage or something like that. So when you have a histogram like this, when the bars are about the same size, we call this uniform distribution. A lot of the most basic one that I do, for example, that I use for this is when you look at, if I was to look at the probability of the theoretical probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6 with one die. So they each have a 1 in 6 chance of occurring. So here I have, what's going on with my drawing lately? Here I have not, so this is 1/6 frequency, right? So if I was to do this a bunch of times, and I would just roll and count how many times I got a 3 or 4 or 5 or 6. In theory, they'd be the exact same. Even if I did this not in theory, but in actual experiment, let's say I did this as an experiment, I would have numbers that would come up about the same. So maybe 2 comes a little bit more than 1, maybe 3 even more than 2, 4 a little bit less, 5 the same, and let's say 6 is a little higher. This is pretty flat, okay? The theoretical probability one here is flat, completely flat. They're all the same height. And this is what we call uniform distribution. In theory, you can get things that are perfectly uniform, right? So they look like something like this when you just take a quick look at them. But in experiments or in practicality, you might just be a little bit up and down. So in either way, if I was to draw lines here and connect these like that, it would look something pretty flat. Okay, and this is what we call uniform distribution, where everything occurs about the same amount. So that's the first type, very straightforward. The second type is normal. Okay, normal distribution, this is called mound. I haven't really heard it called that before. Mound shape or normal shape. It's a bell-shaped curve. So in real life, a lot of things occur this way, and we're going to do a lot more of this when we get to Z-scores in the next unit. So what happens is the mean, median, and mode. Okay, so we'll start talking. We'll go back to about those terms that we had earlier. The mean, median, mode. The central tendencies are all about the same. So what happens here, if I was to look at something like baby weight, okay, and I think the average baby, let's just say the average baby is 7 pounds. And I said, how many babies weigh 7 pounds? We're going to go to the 1/10 of a pound in each case here. So give me 1 second. I'm just going to unplug something. So if I was to do this and I had a bunch of babies and I measured the babies and 7 pounds, I would have a line that would look like this. I have so many babies that are 7 pounds. Just a little bit less, so 7.1 pound or 7 pound 1 ounce. Just be a little lower. Okay, so that histogram bar would be a little lower and a little lower and a little lower, a little lower, a little lower. And once I get to 9 pounds, it'd be even lower. And then on this side here, same sort of thing here, I would have, many, not as many as 7, okay, but I might have 6.9, it might have almost as many, and almost as many, and almost as many, but it gets lower and lower and lower. And when when you look at something like this, or you look at different things, if I was to say to you, why don't you go for a run, a sprint, and then time how many times you are in this interval, that interval, and it's slower and faster, what you'd find is the guy, the tallest guy here is going to be your mode. So the most common is the mode. When you have something like this called a normal distribution, the mean and the median, if you calculated them, would be all about the same. So when you look at something like this, give or take, okay, the mode's the tall guy, and the mean and the median are about the same. And when this takes place, and you were to connect the dots, what you get is what we call a bell curve, or a normal distribution. Pretty symmetrical. It doesn't have to be perfect in real life, but if it has this general shape, we call this a normal distribution. Okay, so that's a normal distribution, which you'll learn a lot about as we move forward. So let me go, that's that one. The next two are, the next one is bimodal. And bimodal has two modes. So two most popular guys. So two tall guys here. They don't have to be the exact same, but you have when you graph this, you have something that looks like this. Okay, it goes up and down. Okay, it has a peak and another peak. This is popular, everything else is less popular. This is called bimodal, two modes. And you see this usually when you're looking at two different pieces of data. So the example I use all the time in class is if you've got all the elephants on Earth and you weighed them. I don't know if you know a lot about elephants, but if you, I also do this with lions. So let's do the elephant example first. If I was to weigh all the elephants, I don't know what the average weight. If I went to, there's two types of elephants. There's Indian elephants and African elephants. Indian elephants weigh less than African elephants. So if I was to measure all the weights of every single Indian elephant, I would have something like this. Okay, I don't know what that would be, but there's your average or your median, and then it would be a normal bell curve based around that central tendency. If I was to then go ahead and do the same thing with all the African elephants, I'm not sure about the numbers, but let's pretend they're about the same. What you would find is a much higher median. I think there's less African elephants, so we'll do something like that, okay? So here, this median's higher, and it would also be a normal curve. But if I said to you, let's see all the elephants and put these together, what you would see is when I added these numbers together, it wouldn't really affect this that much, right? But you would have that, maybe it would level out a bit, but the new guy, if I combine these together, would look something like this. So I'd have two different modes. This is the Indian elephant and the African elephant. Another example I use is if I took all the weights of every lion on Earth, right? You would have you would have all the weights of all the females, and then you'd have the males, which would weigh more. So it's a lower hump because there's less male lions than female lions. But you would have two different modes. This would be kind of generally what you would do is here's the curve for the female lions, and here's the curve for the male lions. And when you add them together, this will get a little higher here, but you have one mode and two modes, so you have two bumps like that. Okay, that's called bimodal. The next two are skewed. So there's two different types. There's skewed left or negatively skewed, and then there's skewed right or positively skewed. So these get confusing because people want to look at this and say, look, this is skewed right because it's pushed to the right. And I understand that. And I used to make the same mistake. But what I like to do is think of it this way. This is you have a normal curve, okay? So you have a normal curve like this. And then what happens is you just have some outliers here, some guys that pull this to the left. So you have a normal curve, and when it's pulled to the left a bit, that's called negatively skewed or skewed left, okay? Pulled to the left, pulled to the left. This example that I always use for this is if I did the class average for marks. So if I had your marks as a class, what happens is it's a normal distribution. Let's say the average is about 75. Okay, so the class average would be about 75 or 80 or something like that. But what happens is we always have a kid or two that they essentially drop the course, but they don't drop the course. So you have some kids that will have very low marks, and they'll pull the average down. They'll pull the median down. So what happens here is the following. You think about this for a second. If I had 80 and 80, if I had all these kids with 80s and 82 and 78 and 77 and all this stuff, right, and 83, and then a kid who never showed up to class and got 1, okay, how this is going to skew, okay, it's going to pull to the left for sure, right? But let's look at the mean, median, mode for a second. If I went, what happens now to the mean, the median, and the mode? Okay, first off, the mode's going to stay the same. My mode's 80, okay? So mode's not really affected by this outlier, okay? The median, the middle guy, might get affected. Right now I'm here. It might move over a little bit, right? So if that's not the middle, in this case here, I think it actually stays the same. But even if it did move a bit, it would just move a tiny bit. But the mean is going to be the guy that's moved over quite a bit. So if I had the class average, right, you guys have probably known this on your test. If you have an 80 on a test, an 80 on a test, 85 on a test, and then you get 3 on a test or 13 on a test, your class average, your own average is going to just plummet, right? It's going to be affected the most. Here, the mean and the median, right? The median here, if that's 80 and 80, right? it's still 80, right? The mode is still 80, but the mean is the one that gets pulled down. So in this case here, one way you know it's skewed left is the mean is less than the median. The mean is pulled down to the left. The opposite happens in what we call a positively skewed distribution. So here, the example I use is if this was the average wage of everyone who works at Walmart, okay? So I get all the average annual wages, salary of everyone who works at Walmart, okay? Not necessarily salary, but how much money they made in a year. And I said, let's get everyone at Walmart. Don't forget the big cheeses who make a lot of money, the CEOs. Now, there's not many of those people, right? But they make a lot of money. So they make a lot more. So they kind of pull this curve over. And what they do, again, is they pull the mean over. So in this case, the mean is going to be greater than the median. The mode doesn't change, right? So this is called skewed right or positively skewed. You're pulling the data to the right. You're pulling the mean to the right. So that's mean, median, mode with respect to all the different skews. I'm going to stop the video here and make another one for box and whisker plots because it's a little bit different. Okay, so hope you got that, and then new video coming.